All right, so let's finish off this lesson 14.4. It's about 10:20 at night for me, um, so this thing will probably get posted probably around 11:30 or so. Um, I don't really have too much of a problem posting it for you guys that at that point in time, since I know most of you just probably stay up till 2 or 3 o'clock in the morning doing homework anyway. Um, if not, you just have to watch it tomorrow. All right, so let's finish off where we were. So we were trying to find the differential of this function, which we did, and then I was kind of giving you this example here that if the actual change of z is delta z, but as x and y changes from 2.1 to 2.03.98, this is just kind of a made-up thing. This would be the actual change right here. So you would do the function's value minus the function's value at the starting point, and you would get approximately negative 0.338. Whereas if we wanted to do dz, which we didn't get to finish in class, oops, dz, according to our differential, is going to be 3 times x, oh, the x is 2, right? Got it. Lost where I was there for a second. 2 squared. And this is just plugging x and y into this equation up here, and then dx and dy are my differentials. So natural log of 1 squared, that's really nice, plus, oh, I'm sorry, times dx. Dx in this case is the change in x. Well, x goes from 2.03, I'm sorry, from 2 to 2.03, so the change in x is 0.03 plus 2 times 2 cubed over 1, 2 times 2 cubed over 1, times dy, the change in y goes from 1 to 0.98, so that is negative 0.02. The good thing is this whole piece right here is going to be 0, because the natural log of 1 is 0. Great, ready to install, thank you. So this whole piece right here is 0, and all I have left is 8 over 1, I'm sorry, 16 over 1 times negative 0.02, which is negative 0.32. This is the differential. Close. Not exactly the same, but a close approximation to this. It's off by, what is that, 18 thousandths. So it's not a huge difference here, but it is, there is a difference, which is why it is called the differential, because it is not the exact. This is the tangent plane approximation. This is the actual change in the z value right here. Okay. We should be able to get the rest of this stuff done, I think, in one video, because the rest of this is actually pretty short. All right, number 6. If z is 5x squared plus y squared and xy changes from 1.2 to 1.05 2.1, compare the values of delta x and dz. So it's kind of what we just did. So let's find dz. Remember that dz is going to be the partial of x, which is 10x dx, plus the partial of y, which is 2y dy. Okay, so dz is going to be 10 times my x value, which is 1, times the change in x. 1 goes from 1 to 1.05, so that's 0.05, plus 2 times the y value, which is 2, times dy. Y goes from 2 to 2.1, so that is 0.1. So this is 10 times 0.05, which is going to be, what, 0.5? This is 4 times 0.1, which is 0.4. So we get 0.9. That is the differential. Now we're going to compare that to the actual change in x. That should actually say delta z, not delta x. Sorry. Get rid of that. That should be delta z. Okay, so let's find delta z. Well, that's the actual change in z. So we actually have to evaluate the function at this point and then subtract the function evaluated at this point. So f of 1.05 comma 2.1 minus f of 1, 2. Alright, so if I plug in 1.05 for x and 2.1 for y into this equation, I'm not going to write all that stuff out, but if I do plug that in, I get 9.9225. If I plug in 1 and 2, we can figure that out pretty easily. That's going to be 5 times 1, which is 5, plus 2 squared is 4, so that's going to be 9. So ultimately what we get from that is 0.9225. Again, a close approximation, not extremely close in this case, because we're off by 0.0225. But this is the actual change. This was the tangent line approximation. That's the differential. All right, moving on. 2 more to go. Okay. Related rates. The length and width of a rectangle are measured as 30 centimeters and 24 centimeters respectively, with an error in measurement of at most 0.1 centimeters in each. Actually, this is not related rates, this is still differentials. Use differentials to estimate maximum error in the calculated error of the rectangle. So, if we want to know, obviously the area of a rectangle is length times width. If we want to take the differential, this is going to be the estimated maximum error. So the differential, it's the derivative of this thing, or the partial with respect to L first, which is just W. And then it's dl. Plus the partial of this thing with respect to W, which is L, and then dW. And let's go ahead and see if we can figure out the information here. So it says that the width is 24. It says an error in measurement of at most 0.1 centimeters. So that's telling me that my DL is going to be at greatest 0.1. So we want to find the maximum area, so we need the greatest possible DL, which is 0.1. The length is measured as 30, and it also has a 0.1 for DW. So we should get 2.4 plus 3, or 5.4, and we are talking about the area, so it was, what is it, centimeters, so it should be centimeters squared. That is the maximum error according to the information given in this. That is my DZ. That is the differential, the maximum possible error in measurement. Alright, one more. Let's see, use differentials to estimate the amount of tin in a closed tin can with diameter 8 centimeters and height 12 centimeters if the tin is 0.04 centimeters thick. That's different. We actually have to deal with a thickness now. Alright, so let's see. Let's go ahead and sketch this tin can. So I'm just going to assume it looks basically like a cylinder. The only difference is, and this is, I'm not going to be able to draw this very well, we're going to try anyway. We have a thickness, so I don't know how to draw the thickness. Maybe something like this. Not too bad. And then of course down the side you also have a thickness on the inside of the can. It's the same thickness, I guess. 0.04 centimeters thick. Alright, so we want to know, according to this, first of all, the volume of a cylinder is pi r squared h. We want to know, estimate the amount of tin in the closed tin can. So the amount of tin is really the outside of this. So why did I use volume in this case? Well, because it does have a thickness to it. Otherwise, it would just be the surface area of a tin can. It does say it's closed. That's important. That means it has a top and a bottom. So I'm going to have not only this top, this bottom down here, but then the outside portion of this. So if we want to take, oops, the differential of the volume, the only reason, again, I'm using volume is because I do have this thickness right here, so it does have a volume to it as opposed to just a surface area. The volume is going to be the derivative of this thing. First of all, it's the partial of r, so that's going to be 2 pi r h, and then times the derivative dr, differential, I'm sorry, of r, plus, and then it's going to be the partial of this thing with respect to h, which is pi r squared, and then times the differential of h, dh. Alright, so we want to find dv, which is 2 pi. It tells us that the radius of this thing, well, it doesn't tell us the radius, it tells us the diameter is 8, but that makes the radius 4. And the height is 12. Then we have to think about this dr. And I've got pi, radius again is 4 squared, and then dh. Okay, so let's think about this. dr is how the radius could potentially change. Well, that's the thickness, because the radius can go, let's try this in red. The radius can go from here, which is the center, out to here, or it can go out to there. And the difference between those two radii is the difference in the thickness here of this can, which is 0.04. So dr is 0.04. And the difference in the height, well, you have a thickness of the can. You're going to have the thickness on the top, so it's also going to have a thickness this way, and it's also going to have a thickness of the bottom. So in this case, the thickness is going to be doubled. So this dh is going to be 0.08. Because again, so if you're thinking about the top, you're going to have this difference in the thickness going up and the difference in the thickness going down. Because you're going to have a thickness, this is really hard to draw, comes around here. So you're either going to stop here or you're going to stop at the top. There's a 0.04 thickness here. Same thing around, whoops, what happened there? Whoa. Let's get out of that. Okay, I'm not sure what is going on. Weird. So again, you've got this thickness coming around the bottom of the can, and it's either going to go down to here or it's going to go all the way down to the bottom, and that difference here is also 0.04. So up at the top is 0.04, up at the bottom is 0.04, so you get 0.08. So let's see what we get. So this is going to be, what, 48 times 2 is 96 times 0.04. So 96 times 0.04 is 3, come on, right, 3.84, oops, pi. And then this one here is going to be 16 times 0.08. Wow. 16 times 0.08 is 1.28 pi. So it looks like we're going to get about 5.12 pi. And this is how the volumes differential is, so it's going to be centimeters cubed. 5.12 pi. And that would be your differential with respect to the volume here. Alright, that's it. That should finish you guys off. Let's see how we did there. A little under 15 minutes, not too bad. All right, shouldn't keep you up too much later. All right, that's it.